Hello, this video clip is about to make up our lecture, which could not be done because of Bayram holiday of our course ELE452 Fundamentals of Medical Imaging. The topic on the seventh week related to magnetic resonance imaging, which is again a non-ionizing imaging, medical imaging modality. So, this lecture is about the general concepts and some physics about it before concentrating on the hardware aspects. So, this is the general view of the system where the patient is placed into the imaging system in a supine or lying down position. There's a patient bed, there's a big hole having a great DC magnetic field. So there's an invisible force in the system which could result in great and damaging forces due to the high strength DC magnetic field. So there are some precautions. Actually, it's a non-ionizing radiation. This is very safe, but its magnetic field and electrical systems requires very special handling and caution during the usage of the system. First, let's explore some physics because some of the system's properties depend on quantum physics. Magnetic resonance imaging, as a verbal definition, relates to magnetic because it's the magnetic or originating from the magnetic properties of the elements. So, quantum spin numbers. Resonance is actually a kind of energy transfer harmony. So you excite some nuclei in the atoms or spins, then you receive the echo or the reflected energy. But it's not light, it's not the same as previous systems like ultrasonics or wave structures. Rather, the energy transfer during the resonance condition, resonance of the two frequencies, resonance of the excitation and resonance of the nuclear responding to that excitation. And finally, we have some calculations, complex arithmetic and matrix equation to yield the image on the screen or save it to the disk in a big data format. So again, it's a two-dimensional MRI parameters display in a matrix form of the body. Well, this is actually a slice imaging format. So you obtain the image of a slice of the body. Of course, you can have three-dimensional volumetric image, so that's a very powerful technique. Also, you have slice or tomographic imaging from this instrument. So let's explore some definition details of the technical parameters. Magnetic means or addresses to a phenomenon related to magnetism. Magnetism is a physics branch dealing with invisible forces between ferromagnetic materials. Electric currents produce magnetic fields and magnetic waves. Wave means it's alternating, but here we do have both high strength DC magnetic field to have some kind of bias to create energy transfer between the nuclear and the system. Plus, we do have alternating current or AC magnetic fields at radio frequency cyclic behavior. Also, we do have a third kind of magnetic field to switch on and off some auxiliary electromagnetic fields in the system. So it's actually unbelievably complex and interdisciplinary imaging system. Let's remember something about general aspects of magnetic fields. We do have two kinds of magnetic field flux density and magnetic field intensity. B, as in units of Tesla, comes from the magnetic flux densities, and H again is related to the magnetic field intensity. So please do not confuse them. Usually B field is our first focused magnetic field parameter in MRI systems. Resonance comes from the harmony when the signal frequency, that's a different magnetic field, radio frequency magnetic fields, frequency equals to the system's spinning nuclei frequency, then imaging can be acquired or performed properly. That's the moment of actual imaging energy interaction takes place. So we need to have a resonance. So these systems obtain the image at resonance. Magnetic resonance imaging systems, formerly means in 1950s or so, nuclear magnetic resonance systems. At that time, it was not for human imaging. At that time, it was for chemical analysis. So the methods or phenomena, nuclear magnetic resonance systems interact to determine the chemical structure of the samples, little samples. They weren't for human imaging purposes. Human imaging applications became later in the years of 70s by applying the same rules of nuclear magnetic resonance. So, formerly nuclear magnetic resonance was called NMR. Um, more than 50 years, today more than 75 years. They were known in a long time. But after 72, it was applied to human or medical imaging area. After this application, commercial or first research magnets about human beings were introduced, but ordinary people out of science or physics were very afraid to hear that the system utilizes nuclear magnetic resonance. So the term nuclear resembled nuclear bombs or radioactivity, which does not occur in these systems. Nuclear in science relates to the nucleus, which is the atom of the elements. There's nothing to be scared of. But the people were so scared, so medical imaging people, doctors, physicists, scientists, etc., omitted the word nuclear, so just called magnetic resonance imaging systems. What are the advantages of the systems compared to other tomographic modalities? First and the best and the most, there's no ionizing radiation. So it's completely safe for the human body. Even pregnant women with babies can be imaged safely. There's no, okay, the energy of the radiation is unbelievably low. Even, well, not as low as ultrasound imaging, but it's really low, lower than visible light systems. Okay? So the other property is uh, human body has very uniform magnetic properties. So the penetration depth of the MR system is really high. So it's better than ultrasound to see deep tissues with the same image quality parameters. Spectroscopy is a branch of NMR showing the chemical structure or surrounding properties of the tissues, which can also be used in MRI, medical imaging topics, but had formerly been used in chemical analysis applications. So the radiation employed in this field, as I told, radio frequency magnetic field excitation. So let's summarize. There's a very high DC magnetic field, always present, even if the machine or imaging is turned off. The second field is for resonance, radio frequency magnetic field, comparatively or very much lower intensity than DC magnetic field, but it's a radio frequency magnetic field. Also, there are switching magnetic fields during the imaging sequences. So, DC magnetic is denoted by B sub 0. B sub 0 denotes a high strength DC magnetic field. Today's systems 1.5 Tesla or 3 Tesla or even more 4 Tesla and up to 12 Tesla research magnets are available. But in the clinical environment, mostly 1.5 or 3 Tesla systems are used. B1 magnetic field is radio frequency magnetic field, much lower than that B0 field in the peak intensity, but its frequency is in the radio frequency range from about 60 megahertz up to 126 megahertz with the known constant of frequency related to the magnetic field we will see later. So what's happening in magnetic fields can be inspected in single atomic scale. If you look at some nucleus and electronic structure of single atom, each electron has 4 different quantum numbers. The fourth one is magnetic spin. So it can have some discrete properties, and it will not be thoroughly explained in this lecture. And the most important element for MRI is water or hydrogen atom or proton. So proton spins around itself, so creates its own magnetic dipole moment. So it's like a rotating charge accumulation. If charge moves or rotates, then it creates a magnetic field around it. So that's the principle of all magnetic sensitive or possible elements. There are some odd number of magnetic spin elements like hydrogen or phosphor or some other elements are MR possible elements. The others cannot create that spin, cannot reflect magnetic spin energy. For medical imaging, only hydrogen or proton is valuable for imaging purposes, anatomical imaging purposes. Okay? So, the source of magnetic energy is, magnetic parameter energy is spinning proton. So this figure is borrowed from your online textbook. Hydrogen says that hydrogen nuclei are used for MRI because their magnetic susceptibility and other parameters and their vast amount of concentration in the human body. Proton is everywhere in the body, in our bloodstream, in our tissues, in our fat tissues, brain, everything. More than 70% of our body is water, and other tissue biochemical molecules all are hydrocarbons, again have hydrogen, but in different molecular environment. That difference in molecular environment creates the contrast between tissues, and this shows medical experts the conditions of our body. So each spin little nucleus is like a little compass. So that's a nice analogy. Okay, so it rotates or aligns itself with the main or DC magnetic field. But different from the compass, okay, it cannot align fully due to the rules of the quantum mechanics, which will not be explained here. You can only have either align with some certain angle or anti-align with negative of that certain angle. So only element with odd multiples of spin number can have desired MR properties. MR property means they transmit back the MRI energy sent by the radio frequency coil or antenna. Radio frequency excitation is transmitted. These MR sensitive nuclei responds back at the resonance condition. So this is the requirement for MR imaging. We have normal water or fat or organic molecules which contain hydrogen. So this is the situation of a group of protons in the body. So at the left side, marked with 1 here, we do have nuclei in random orientation. There's no strong magnetic field, so they are randomly oriented. There's no net, let's say, direction or alignment of the protons in terms of their spins. When this body is placed in a strong magnetic field, B0 magnetic field, up to 3 Tesla, you see, according to their quantum properties and random distributions, some of them align into the through the field direction, but not completely aligned. So there's an angle theta. Okay, that's quantum mechanical law. Some of them anti-align. So there's a net difference between the aligned and anti-aligned nuclear population, and this difference, like 1 in a million, create that very low microvolt level MRI signal. But that's again enough to form the image. So in terms of energy band diagrams, this can be also shown in the following, this image. So the population of anti-aligned nuclei have slightly higher energy. The population of aligned spins do have slightly higher population but lower energy. In the nature, the rule is always applies. Every physical system tend to lower their energy to become more stable. So in the room temperature, some nuclei gain some energy from ambient and increases the energy to a little bit higher level, anti-align, and some of them lose their energy to be in the aligned case, and under high DC magnetic field, there is a population slightly greater in the aligned case. The energy difference between these two states can be given by known constants of gamma, gyromagnetic constant, H, Planck's constant, B0, DC magnetic field, and 4 pi. So that gamma requires attention of ours because that gamma determines the MR resonant frequency. So this is another nice illustration for the population of spins. When they are in random, you can have, okay, we don't deal with single atoms. Rather, we deal with a big population of atoms in the body. So we can express the whole behavior of the population of atoms as a net resultant magnetic field vector. So on the left side, there's if you add up all spin vectors, then we can have almost zero net magnetic field inside the body. But when we place these nuclei in a high strength magnetic field, then they align or anti-align, and perform complex movements like precession, etc. But their resultant vector completely aligns with the B0 system. So each little nuclei cannot align properly, but their cumulative sum can be aligned. And this cumulative sum is shown with letter M, magnetization vector of the body. So this is a like reaction magnetization vector to the outside DC magnetic field B0. What happens when we excite that M? Okay, M this time represents Avogadro's number or bigger number, 10 to the power 23 or 24 spins of our body. If we send an excitation from outside, which is B1 orthogonally, that means we apply torque. As soon as M flips away from B0, it starts to precess around B0. That's the law of the precession. So let's stop at that precession to come later. I told that gamma has a specific meaning for ourselves. For hydrogen, gamma is 42.55 or roughly 42.6 megahertz per Tesla. That means for each Tesla DC magnetic field, you have to apply radio frequency of 42.6 megahertz to excite the nuclei in a proper form to get the MRI image. So that's a magic number you should know, 42.57 or so megahertz per Tesla. And this is the formula for the frequency of excitation. This is called special Larmor frequency. For MRI, that's required. You have to apply exactly this frequency to excite the nuclei in the body, and the systems are tuned, antennas of the systems are tuned at that frequency for transmit and receive electromagnetic excitation. So after you send this energy, the tissues reflect back their own magnetic signals, magnetic resonance signals. This signal is called free induction decay or FID signal. So we stimulate with Larmor frequency and the tissues reflect back with FID signal. That FID signal has amplitude, attenuation, phase difference, lots of information to be decoded, and this information is used to image. This is a nice illustration at the time of excitation. As soon as you send the excitation, the magnetization vector starts to precess according to the rule. So there's a kind of rotation of, let's say, an invisible or let's say virtual environment in the tissues. That rotation, if you observe the rotation, this is like a decaying exponential sinusoid from outside. If you look at the same waveform or magnetic field vectors B0 and M inside the rotating environment, then you see only a flipping and then returning back magnetization vector M. Okay, so that's about the issue of rotating frame reference. Anyway, so now we have a DC magnetic field, static magnetic field B0, as well as the response to that static magnetic field by the spins of the tissues or body with a cumulative magnetic field, invisible magnetic field, M, magnetization vector. So all magnetic resonance imaging systems, technical people concentrate on B0, B1, and M field. So we don't care about individual tiny little hydrogen protons or whatever, okay? M field. So we concentrate or show all the body activity with M vector. So this is a conceptual expression of the M vector where number of tiny little spins up from 1 to capital N, N goes to almost infinity. So individual spins are added and our magnetic field response of our body is expressed. So B1 field is applied through an electromagnetic antenna towards the field, and that field is a sinusoid orthogonal in the so-called transverse plane to flip that M vector. If you apply another magnetic field orthogonal to the first magnetic field, you change its orientation. If you are in the same frequency as the rotation, then you continuously apply that rotating field to the M vector. So this is the trick or secret. That's the reason of the resonance. So B1 field frequency is exactly the same as Larmor frequency of the system. So this is a very nice basic diagram of the signals where the shaded region or during that interval transmitting energy is applied through the antenna, radio frequency antenna. Then this antenna is transmit part is switched off. It behaves like a receiver antenna, exactly the same as ultrasonic imaging. The same piezoelectric sensor is used to send the pulse, then it's switched off or multiplexed to receive the uh, reflected pulse for electronic preamplification, etc. That happens in the MR exactly the same, only the type of electronic devices or sensors are different. Here, our sensor is electromagnetic antenna or RF antenna, radio frequency antenna. So this is the basically pre-induction decay. It freely decays exponentially, it is attenuated, and the signal carries lots of information in terms of its frequency, its decay constant, phase. Those are all decoded to reveal the image. That's a little bit complex concept. I try to or want to summarize general aspects. Otherwise, it's really complex, and the analysis of these decaying things requires a graduate course, so it's not the place for you to learn all the details. Basic things. MR images contain three parameters to be imaged. Remember, older images, visible light images rely on visible light reflection or transmission. Ultrasonic systems rely on acoustical impedance and attenuation and the speed of the acoustic waves in the tissues to determine the boundaries and contrast, etc. Similarly and differently, MR systems rely on first, how many protons are there in a per cubic volume? The more protons you have, more water means more signal. For example, bones or skull contains much less water, so they can send less signal. Air in the lungs, again, almost no water in the lungs, so very little signal is observed. But other tissues, especially soft tissues, um, are shown with very high signals in the MR images. Second parameter to be imaged is called T1 relaxation. Relaxation means When you flip or excite the magnetization vector in the body, when you flip M, it returns to the original situation in two different time constants. First is called longitudinal or z-axis or main axis or B0 axis. So that's in T1 time constant. That's an exponential um, initialization to or returning back to original state. So it's one axis is T1. The transverse axis, XY plane relaxation is occurs in a different time constant. So it's not like an ordinary vector is rotating back. No. First, transverse axis diminishes to zero, then z-axis increases. So the M vector relaxation is a bit complex nature. So we do have two different constants. One is along original axis, the other one is perpendicular to the plane of the axis. Okay, that's called T2. All the images, there's a kind of weighting in these three parameters. Some are many images can be taken for or to reflect proton density. Some images you can adjust some MR parameters such that the image are very sensitive to T1 relaxation parameter or T2 or a combination of all these three. Again, that depends on particular inspection or diagnosis purposes of the medical experts. So let's look at some values, average values of proton densities. You see muscles, either skeletal muscles or heart muscles. Those are the highest water content. Inner organs, kidney again is full of water to filter out the bloodstream, etc. Those are high. But bone structures, they have very little water content, okay, as I told. They are mostly inorganic. And T1 relaxation for uh, arbitrarily consider two tissues A and B. If tissues are different, of course, their T1 relaxations are different. So that means tissue A has a lower T1 constant, means that our M vector easily returns back to the original situation or condition faster than tissue B. So their signal strengths is the same at the initial condition, almost the same at final condition, but in different, in let's say intermittent time instance, their signal strengths are quite different. That means the contrast is the maximum. So MR specialists adjust the parameter to receive the signal at those instants, not before, not later, to have the maximum contrast. So that's the aim. Similarly, T2 relaxation is diminishing in the transverse plane or XY plane. So that's a kind of decaying exponential. Again, tissues A and B, the signals are almost the same in very, at time T0 or right after the excitation, outer excitation. Again, these two tissues are almost zero signal at a very long time later, but their signal difference between these curves are highest in the intermittent time. So again, MR signal acquisition parameters are adjusted such that the signal is obtained at these times to maximize T2, so-called T2 contrast moments, okay? So there is a table of comparison of different tissues for 0.2 Tesla. Remember that all relaxation parameters or MR parameters also depend on main high DC fields. So this table represents the conditions of different tissues. You see, Generally, T1 time constant is much longer than T2 time constant. Why? Because T2 depends on surrounding molecular structure, so it's really uh, much affected than surrounding tissues. That's the reason T2 is much lower. So T2 or transfer planes relaxation or becomes zero in a very short time compared to T1 relaxation. So, of course, these are experimentally measured values. There are experimental errors. There is no direct mathematical standard calculation for time constants. That's human dependent, conditions dependent. So, there's a big range of values of these MR parameters. Also, T1, T2 relaxation at today's systems, 1.5 and 3 Tesla systems, consider differently than zero point 0.2 Tesla systems, which is expectable. So this table is much informative. It gives T1 at 1.5 Tesla. Again, the same. You see, for particularly brain has almost 800 millisecond for T1 relaxation, but much more value, 1,100 values for 3 Tesla systems. And the rule is almost the same. T2 relaxation time constant is much smaller than T1 again. So it's good to define the acquisition mode, one or two time constant times for T2 relaxation, etc. And these are illustrative summary of T1 and T2 relaxation signal strengths for any person under MRI investigation. M0 is the cumulative magnetization vector of the body, and when it's flipped, the signal becomes zero at the first instant, but later its z-axis or main field aligned values relaxation or goes to the original state after and first order differential equation exponential time constant. So this is related to T1, the first curve on the left side. Second curve at the right side relates to the T2 relaxation, which is much smaller. You can compare T1 of 1000, 2000, up to 3000 milliseconds are okay or applicable for T1s, and much lower 45 millisecond, 100 or 200 millisecond T2 time constants, which is from maximum signal to the zero signal at the transverse plane, can be observed. Okay? So 5T2 is assumed to be in the steady state of initial condition arrival. Uh, so we can assume that after 5T1 or 5T2, we reach to the again initial conditions properly. So MR systems utilize these physical phenomena and has three parameters to create image and create contrast of the body. These three parameters are proton density, how many proton particles inside the body, and their net spins and form the M vector. So if your M vector is strong, that means more molecules, then you have good MR signals. Second, T1 and T2 relaxations in so-called longitudinal axis. Longitudinal means the same direction of the B0 DC high magnetic field and its transverse plane. Transverse plane means XY plane orthogonal to the system. So in these two directions, we have two different time constants to be imaged. And all the images are a weighted combination of proton density T1 relaxation and T2 relaxation. So the best signal acquisition times are the most contrast moments in two neighboring tissues, and radiologists or experts arrange imaging sequences according to it. We will explore the imaging details in the next week's slides. So we have borrowed information from our online book as well as an older textbook. And thanks for watching, listening, and contributing. Please do not forget to do homeworks and perform self studies to increase your experience in the topics. So take care.